Okay, welcome everyone to the last session of today. So we're going to have overview talks from 8 different telescopes / collaborations. I just want to mention there were 2 things, but I can't remember the second one. But okay, so it's a catch box, not a drop box. So we're going to implement some new rules. That wasn't me who came up with that. Someone else acted, and I thought that was funny. So please don't throw the catch box the whole length of the theatre. We're going to do halfway at a time. I think that is far more reasonable. As fun as it may be, we won't like it. We would like it not to break. And that also, please don't shy away from it. So if you're only throwing it halfway, the throw isn't going to be as hard. It is not going to hurt you. So please catch it. I know none of us are like pro baseball players. That's why we're here. And so there was also another thing. Oh, yes, it doesn't connect to the speakers. So when you're asking your question, can you make sure you really project your voice, or ask the speaker, like the presenter, to repeat your question so everyone else can hear? Does that sound good by everyone? Cool. Yes. Awesome. Like the thumbs up. Thank you. So yeah, we'll now start with our first speaker of this session. Yuanming Wang will be talking about the ASKAP craft / cracker system, and I'll give you a 2-minute warning. Is that all right?
Yeah, thank you. Okay, thanks everyone. So I'm Yuanming Wang, and I'm a postdoc working at the Sweden University. So today I'm going to introduce the ASKAP Craft Crackle survey on behalf of the Craft Crackle collaboration. The telescope we are using is ASKAP, which is a wide field survey telescope located in Western Australia. Specifically, it's in MRO observatory. And ASKAP have 36 antennas, which arranged in a way to provide good imaging capability and also can do precise localization. So ASKAP also confirm 36 simultaneously overlapping beams at the same time. To combine all these 36 beams, we're able to get a larger field of view, which is about 30 square degrees. So combine all these advantages with good localization precision, large field of view, and the relatively high sensitivity. ASKAP is very good for to conduct untargeted transient search. We started the craft incoherent sum ICS survey from 2018. And the survey is to find millisecond bursts in real time with precise localization. So here is a workflow. From each digital beamformer, we get the total power summed over polarization and average them into 1 megahertz and 1 millisecond resolution. Because we have 36 beams, so we are getting 36 intensity time series data streams from the beamformer, from each digital beamformer, and conduct the FRB search. We will get the search pipeline will provide a list of candidates, and we will use this list of candidates to triggering the raw data voltage downloads. The voltage have 1 nanosecond time resolution and full polarization. Because ASKAP can save about 3-second buffers, that means all the search needs to be finished within 3 seconds. After we have the voltages, we have the CDB pipeline to do the calibration and imaging, and then localize the FRB. Once we have the FRB localization, we will conduct the optical and infrared follow-up using VLT, Gemini, and CAC observation to identify the host galaxy and study the host galaxy properties. So craft and crackle survey is fully commensurate with ASKAP other large surveys, which means we generally do not have a lot of control of where we are pointing. Here is the exposure map of the craft ICS survey. You can see some field has been longer monitoring than the other field. For example, the ASKAP bandpass calibrator field, 1934, we observed it more than 1,000 hours and found 1 FRB in that field. And until the end of 2023, we have total about 15,000 hours observation. And the FRB detection rate is about 0.05 FRB per day. So ASKAP have 3 different frequencies, and in low frequency, mid, and high. we are a bit more efficient in a low frequency, which is about 900 megahertz compared to the other frequency. So we'll also highlight some craft science. Since we're able to localize the FRB, the first time ASKAP, so ASKAP localized the first one of FRBs, and which is at a massive galaxy, which is quite different from the first repeating FRB 121102, which is in a dwarf galaxy. And after that, we started accumulate more and more localized FRB, and we provide the first large sample of localized FRB. So we can use them to study their host galaxy properties, and we found the majority of FRBs are from star-forming galaxies and trace the star-forming main sequence. We can also use these localized FRBs to study the intergalactic medium or solving the missing barons problem, as mentioned in previous talk. So to enable to do more useful science on the host galaxy side and also the extragalactic matter side, we want to find more FRBs. That's why we start the Krakow survey, which is the ASKAP craft coherent upgrade. So Krakow is started commissioning from 2023, which is an image plan transient search. So we are doing coherent image. That means we will improve the sensitivity by 5 times, which is quite good. So again, for Krakow survey, from the digital beamformer, instead of getting simple intensity time domain time series data, we are getting the correlated visibilities and average them into 1 megahertz and design time resolution. So we are using the 30 inner antennas of ASKAP, and also we have 288 frequency channels. That will give us about 130,000 measurement data points per time step. And we'll send all this data for pre-processing and then send them into the search pipeline. The data size will be further increased during the search pipeline because we are using a range of de-dispersion trials and boxcar weights trials. And also we grid the data into a fixed spatial size, and then we perform the fast Fourier transform, convert them into image. So for the search pipeline, all of this process, the data volume is about 20 terabytes per second. That is the data we need to deal with. And from that data volume, we roughly get 10 to the 7 raw candidates per day, which is a huge number, and we can't inspect them thoroughly. That's why we developed a candidate pipeline. So the candidate pipeline will do the clustering to group similar candidates and do the basic classification and filtering all the known objects. After the candidates pipeline, we will get less than 10 final candidates per day, which is pretty good. So for that final candidates, again, we will use them to triggering the raw data voltage, which is a which is the same system we use in the craft ICS survey. And the voltage data, again, it is 1 nanosecond and full polarization. So we save the 1-bit voltage data. That means ASKAP can save about 12 seconds in the data in buffers. That means all the pre-processing, search pipeline, and candidate pipeline needs to be finished within 12 seconds to enable the real-time triggering, which is a lot of data. And after we have the voltages, again, we will use the CDB pipeline as what we used before in the craft ICS system to do the calibration, imaging, and localization, and perform the optical infrared follow-up to identify the host galaxy and study their properties. So until last month, the Krakow commissioning, totally we have more than 6,000 hours. And the FRB detection rate is about 0.14 FRB per day. And again, similar to craft survey, Krakow is also fully commensurate with other ASKAP large surveys. So we have some fields which we have the longer integration time. And also we have our own failure time. So that is time, that is the field defined by the Krakow craft team and can be observed during the between of the large observations. So we have different phases in the commissioning. So before 2024 May, we are in the offline mode, running in 110 millisecond and 14 millisecond mode. After 2024 May, we are running in real-time mode, which will enable us to do to trigger the downloading of the voltage data. And in the real-time mode, we are running in 40 millisecond mode and 3 millisecond mode. The discovery rate of FRB compared to the Craft ICS survey is improved by a factor of 3, which is good, but this is still lower than what we expected. So we are still working on technical improvements. With the Krakow FRBs, so here is the plot showing the DM of excluding the galactic component and also the redshift of all the ICS and Krakow FRBs found to date. So we found quite a lot of FRB in this redshift, about less than 1, and this will provide us quite good cosmological constraints. And we also found the repeating FRBs. We found 6 pulses over 1 minute. And here is the super scattered FRB. We found the weight is about 1 second, so very wide. And our modeling showing this is scattered by its host galaxy. Krakow can also do some galactic science. We found about 30 rotating radio transients. So here is the comparison between Krakow RS and the non-RS population. So we can see the Krakow RS in general have the lower DM compared to the RS population, which is not unexpected as image plane search will not limited by the lower DM cut. We also found a pulsar, which is about 40 seconds rotation period, so very long compared to the normal pulsar, which is less than 10 seconds. We also found other long period transients. We have found the 44 minutes long period transients with X-ray emission has been first detected. We also found the 6.5 hour long period transients with interpulse has been detected. Instead of all these astronomical objects, we also detect a nanosecond pulse from the dead satellite. And the DM of that signal is very near to 0. So that means in the normal time domain search, this is RFI for sure. All this work because of the team collaboration across of the world. So we have a different people working on different parts, working on operation, commissioning, post-processing analysis, and also multi-wavelength observation. So you will be hearing the talks from some of the people in this week and hope you can enjoy it. So this is a summary of the ASKAP Craft Krakow. We localize the first one of FRB, and we provide a large sample of localized FRB to use them to study the host galaxy properties and intergalactic medium. We are currently upgrading to Krakow system with improved sensitivity. That means we will find more FRBs. And Krakow can also discover the galactic objects like RS, long period transients, and we're using them to study the galactic science. I'll stop here and thank you.
Any questions? Definitely silence. Who has the catch? Oh, ball.
Yeah. Hi, it's Matt Tubbs. I'm wondering if you can speculate on the lower than expected improvement through Krakow. What's causing that? And certainly you must be sensitive to a different underlying population of FRBs. And so I wonder to what extent that can play a role.
Yeah, that's a very good question. So from the image, so Krakow is doing the image plan search. And the image plan search, the first, as what I mentioned before, we are not limited by the DM card. That's why we can find the galactic object and even the satellite. And the second is from the imaging plan detection. So if we are using the time resolution, like for example, 40 milliseconds or even longer, so we're able to detect the wider object, no matter it is FRB or the other object. So that is another advantage compared to the other survey, but it also depends on what time resolution we are using in the current survey.
We have an online question, so pass it over his capacity. Seth?
I have this question for you. In one of your plots, you showed the pulse width is 1 second. Then for 1 second, because normally is millisecond, is not the large pulse width.
Sorry, are you talking about the super scattered FRB?
Yeah, the one of the last plot you showed.
Oh, yes. So
what is the,
I don't know how to go back.
yeah,
Here.
I think this one.
This plot, right?
Yeah. What is energy? And then here we have 1 second, yeah? What is, do you have any
Yeah.
value for energy or luminosity, for example?
Sorry, I cannot think about the number. So if you just send a message in the Slack, I think I and my other colleague, Yosha, who is leading this work, will have the further discussion.
Yeah, because mostly that's the part with is millisecond. 1 second is very interesting. Thank you very much. Anyways, thank you.
Thanks.
Cool. I think we will move on to our next talk. So let's thank the speaker again. So our next speaker is Sujin talking on behalf of the BURSTT collaboration. And I'll give you a 2-minute warning.
Can you hear me? Okay. Hi, everyone. I'm Sujin, a postdoc from in HIA in Taiwan. And it's a great pleasure to introduce our BURSTT instrument alongside the great instruments for FRBs. And BURSTT is focused on the detecting nearby FRBs, which we believe hold a great potential for unlocking the physics of FRBs. So let me start from highlighting the 3 key challenges from the previous FRB surveys: the low detection probability and the limited localization capability, which the CHIME and the DSA or FS is now already giving a dramatic increase of the FRB detection rate and also increased rate of the localization sources. But because of the limited field of view, we still have kind of missing a lot of repeaters or detectable FRBs, and also missing the host galaxies for the single events. And also the known FRBs are quite far, I think very far, to perform the multi-messenger observation, especially in optical and X-ray telescope. So it also hinders the redshift measurement for all of that. So this BURSTT is launched to solve, to answer these challenges. So it is a dedicated FRB instruments initiated in Taiwan and also expanding to East Asia right now. So we aim to detect the FRBs and repeaters with a very wide field of view, and also the localized it promptly right after the detection, and also focus on the nearby sources to make it possible to perform the multi-messenger follow-ups. So before explaining the specs of the BURSTT, I'd like to highlight the importance of the nearby FRBs. So first, so far the host galaxies and the source environment is not, the contribution of the source and the host environment is highly poorly constrained. So how can I say? So if the FRB is closer to us, it's much easier to separate out the DM contribution of the IGN. So we assume that we believe that the more nearby FRBs can help to constrain and also refine the models for the high redshift FRBs. So I have a jet lag, so I've just started slightly sleepy and try to make it awake for myself. And also, as you know, that for the thinking of the SGR 1935, where we found the X-ray counterparts because it is nearby. And if we have more nearby sources, it is more possible to detect the multi-messenger signals. And also nearby FRBs have better possibility to detect the follow-up burst and the follow-up pulses probably. So we can increase the rate of the repeaters. So let me move on to the BURSTT specs. So the BURSTT wide field of view can be provided by our LPDA array that covers from 300 to 800 megahertz. So the antennas on the bottom is the 3 types that we are using now. And the third one, I can use my mouse cursor here. But the third one with the black one is the one that we are using right now for the main station. So this is sensitive above 400 megahertz. So now we are switching our antennas from black commercial antennas to the custom built antennas, which is on the first one, to reach down to the 300 megahertz. And the middle one is also our own design, which has a better durability and weather resistance, and also being used in one of our outrigger stations. So on the right side, we are comparing our field of view with CHIME. So at least we have at least 20 times larger than field of view than the CHIME, and it could be kind of trade-off. So where we're giving up some sensitivity with exchange to for the wide field of view, so we can cover the 1/4 of the sky at once. So, and our beamform architecture can help us, allows us to effectively scan our wide field of view. So this figure shows our current beamform beam distributions. So now we are using 256 antennas at the main station by forming the 16 by 16 beams. And the east-west direct east-west beams are formed on FPGA, and the data will be transferred to our CPU servers to form the north-south beams. And both of them are conducted in real time. So the current beam size of our at the main station is 2.5 times 5 square degree, and we are planning to shrink this to have to better with higher beam density by increasing the number of the antennas. And for each beam, we perform the real-time search, pulse search at the main station where we have the high sensitivity. And we use the bonsai for pulse search, which is developed by the CHIME team with a 1 millisecond time resolution and 16K frequency channels across 400 frequency band. Our DM search range extends to 1900 parsec per cubic centimeter, which is exceeding our original goal of 1000. So on the right, we are showing the real-time detection of the red giant pulse in the DM time plot, and the bottom one is the zoom-in plot. So because the data rate is high, it's just about 200 gigabytes per second from 256 antennas, we are not saving out the old data, but each station have a 40-second ring buffer. So once the main station got a detection of the burst or FRB targets, we sent out the triggers immediately to all the outrigger stations, and each station will gonna dump both baseband and the intensity data for that, depending on the DM, which will be used for the VLBI localizations. So the main station is located in the Fusan Botanical Garden in northern Taiwan, and we are now operating 256 antennas and the continuous real-time pulse search at the station. So we are also planning to increase, double up the antenna array to 512 in a few months. So we can cover, we can have a better sensitivity and also cover wider field in the sky. And for the outrigger station in Taiwan, we are planning to, and we already have, and also planning to have more outrigger stations. So 2 of them in the central Taiwan and also on the Green Island, we have, they are already operational. And also we have completed site surveys in some of the places in Taiwan for future expansion sites, which is marked with a blue color. So currently the longest operational baseline of the burst is 230 kilometer, which gives us a 0.7 arcsecond precision at 400 megahertz. And to increase our localization precision, we also established outrigger station on the wall in Hawaii and Japan and India. So they already have some of the burst antennas. And also, so from burst Taiwan and Hawaii, we can achieve the precision of 0.02 arcsecond precision in east-west baseline. And you may notice that they are basically located in the east-west baseline. So to have the security north-side baseline, we are now settling up a site in South Korea. And also we visited Mongolia just a few days ago to have for the RFI survey and got a very promising results and found a good place to put our antennas. And also together with NARID, we also exploring some candidate sites around the TNRT. And the burst antennas are simple and cost-effective and really easy to deploy. So we are welcoming any partners who would like to host our outrigger stations for VLBI. So from now, for the remaining time, I'd like to show our performance. And this is the 16 by 16 pixel sky view from the burst. So on the left side, we are showing the sun is moving from in the third row from the bottom, and it is moving from east to west. And we can also see some clear visible side length. And on the right side, it is Cygnus A plus galactic plane. So if you see the in the middle is moving from left to right, is Cygnus A. And also we can see that the galactic plane moving diagonally in the frame. So using the radio calibrators, including the Cygnus A and the Tau A, we measure our SEFD is around 12 kilojansky, which is twice higher than our original expectation. And we suspect that this might be related to the antenna degradation because we put that antenna for years. So, and also possibly some combination of factors that we are now investigating. So on the right side, it is showing the detection rate of the many facilities. And the burst 256 was calculated from our initial design. So the actual burst at this moment is actually located in the right side on the lower sensitivity parts. But we are now, that is for now, but we are now replacing our antennas with a higher gain models. So gradually improving the SEFD, and also plan to expand the array size to twice, and also optimizing the beamforming. So we expect that we can reduce, make the burst location to come back to the original or have better places. So, and the real-time search status is ongoing well. So we started the full beam search from mid-May, and to increase the detection rate, we are now shrinking our field of view to 3,000 square degrees. So, and detecting the, every day we are detecting the single pulses from 0329 and also some of the giant pulses. So on the bottom, we are showing the plot, which shows the beam map and the DM time plot and the dispersed waterfall, which is generated right after the trigger is sent. So we can monitor our triggers right after we detect some, the first main station detects some pulse or FRB signals. And the localization test is also ongoing. So this is showing the cross correlations of the many single pulses from 0329. And I'm sorry that I didn't show the giant pulse cross correlation results here. But what we found so far is that a residual delay from the single pulses from 0329, the residual delay is consistent with our ionospheric expectation within 2 nanoseconds. And we are trying to improve this more with GNSS data. And also we recently found that working on the improvement of the cross correlation SNR by re-beamforming the giant data. So there will be a lot of updates from in the perspective of VLBI. So please stay tuned for this. So I think I'm almost done. So BURST is unique and a quite interesting design. So we believe that BURST can answer some of the key questions for FRBs, such as whether all FRBs are repeaters, and also where there will be more multi-messenger counterparts of FRB, and the third, the contribution of the source and the host environment, host galaxies for their DM. So this is not only from the BURST, but it requires a close collaborations with high sensitivity follow-up instruments that many of you are involved in. So we are really welcoming, we are happy to discuss and collaborate all together. So please reach out, feel free to reach out us if you think that you have something interesting to work with BURST. So we have many things ongoing, and I think I covered some of them. And there are more on the way, including the 2 polarization recordings and also machine learning classifications for fast FRB determinations. So please allow me to skip the details, but I wanted to mention that everything for BURST is working pretty well. So, but we haven't got the FRB detection yet, but we have a giant pulse and a single pulse detection. So the FRB detection might be very soon. So hopefully during this conference. So if I get a detection, I'm gonna dance and then sing here. Yeah. So Okay, so this is all for first, and thanks for your attention, and please stay tuned for our project. Thanks a lot.
Okay, thank you so much. Do we have any Jason? Oh, Jason. Okay. We'll go somewhere on this page. Oh, sorry. That was a terrible throw. That was. It's got to keep going back.
Okay, sorry for asking a question. Very nice talk. Very exciting. I hope you do find an FRB sometime this week. I was wondering, so in terms of using commercial hardware, what is the difference in sensitivity compared to your custom designed hardware, and kind of like what are the lessons that you've learned from that? Like what were the main limitations?
Oh, right. The reason that we started from the commercial antennas is that we took much more time for designing our own antennas, and the price is way cheaper to use the commercial antenna. And first we thought that it is, the technical, the sensitivity SCF of the commercial antennas is higher than the usual, but after we deployed the commercial antennas, we found that the performance is not very good compared to our expectation, and our designs, our antennas, we can reduce the cost for our antenna own designs. So.
Okay, yeah, maybe we can talk at the coffee break. I'm curious in more detail what specifically is the.
Sure, I
issue.
think
Yeah.
the CHIME in Canada, I suddenly forgot the name, but we are also using the similar LPD antenna around.
In Algonquin, yeah.
It's Algonquin.
Yeah.
Is there any questions online? If not, oh, Kelly has a question. There you go. Doesn't have to go far at all.
Thank God.
This is Kelly Gorgie from CSIRO. Yeah, great talk. It's really exciting to see how things are progressing. I was wondering if you could comment on the potential prospects of long period transient discovery. Long period transients.
Oh, right. That's an important question. And we are also planning to see more whether we can also work on the long period transients. But as you know that our sensitivity might not be very enough to detect the single pulses from them if they are not bright enough. And also our ring buffer has a 40-second duration. So if we keep the current ring buffer size, it might be slightly tricky at this moment, but probably by saving the long-term intensity data for the candidates of the long period transient, maybe we can save out and do the offline search separately. That is one of our plans.
Great, thanks.
Cool. Any other questions can be asked on Slack. Sorry, Vicky, we're running behind. But yeah, you'll be available on Slack for any other questions. So let's thank our speaker again.
Thanks.
So our next speaker is Ziggy Pleunis from who's going to be talking about CHIME FRB. And thank you, Mason, for big tech wisdom. You have to wear the Brittany microphone. And I'll give you a 2-minute warning. Yep. All right. It goes around you. Yes.
Okay. No. This doesn't go any further, right? Oh. Okay. Well, hello everyone. Thanks to the organizers for inviting me to give this talk. It's an instrument overview on CHIME FRB that you can see here in the background. And this is a talk on behalf of this wonderful team. Many of us are here at the meeting, so please come talk to us and ask all your questions about how to interpret or use the data. So CHIME is located in British Columbia in the west of Canada. It's in this natural valley, and so the hills around it naturally protected from the RFI environment of the neighboring towns, which is great. You can see CHIME here on the telescope. It's at the Dominion Radio Astrophysical Observatory that also hosts a range of other telescopes, so there's lots of expertise on site. If we zoom in a different season, you can see one of the 4 cylinders that make up CHIME. It's a unique design. It focuses light in the east-west direction, but it can basically see horizon to horizon in the north-south direction. And on this focal line here, you can see there's 256 dual polarization antennas. And so CHIME is an interferometer. just sits there and looks at the sky as the Earth rotates. And because of the interferometric aspect, we can beamform in different directions by applying different delays. And CHIME operates from 400 to 800 megahertz, which was originally set by the cosmology experiment that runs on the telescope as well. But it turns out to be a very unique range to look at FRB. So we probe a different population probably than the L-band surveys, where we are very sensitive to propagation effects, but not yet killed by things like scattering. And CHIME recently got an upgrade. So we built these 3 extra mini CHIMEs across North America to do VLBI. I'll talk more about that at the end of the talk. And the way that CHIME does its detection is, so the instantaneous field of view that you can see here on the top right is about 200 square degrees. We make 16 channels over 16,000 channels over 400 megahertz. We search the data in about 1 millisecond time resolution, and we use 3D dispersion up to DMs of about 13,000. And so within this primary field of view of the CHIME beam, we make about 1,024 digital beams. And so it's essentially as if you're using the GBT, the Green Bank telescope, 1,024 times. So that gives you great mapping speed for detecting lots of fast radio bursts. And the other strength is that we try to be on sky 24/7 and year round. It doesn't always work because sometimes snow accumulates on the dish, for example, in winter. And in the summer, it gets really hot because it's essentially in a desert. And the other strength is because we revisit the same sky every day, that we're very good at picking up repeating sources. And so the way FRB detection works, so the voltage data coming from 1,024 antennas and 2 polarization is about 6.5 terabits per second. And this is beamformed in a correlator, and the search backend then finds the triggers. And the whole, we can of course not store all the 6.5 terabits per second 24/7 year round. And so the whole game is to recognize in real time automatically if one particular few milliseconds of data is worth saving. And we do that by sending a trigger to the 40-second ring buffer that's there to save the data. But most of the data, so we really save less than 1% of data every day, and the rest is all just immediately thrown away. And how this works with the outrigger stations, they're basically just passive receivers. They don't do any FRB searching. That's all done by the main CHIME station. But the outriggers all have their own buffer. They're longer than 40 seconds because they have less antennas. But they just wait there until they get a trigger from CHIME, and then they save the data to disk. So in terms of FRB characterization, first I want to talk a little bit about repeater identification. So the detection rate is quite high. It's about 1.5 sources per day, or it is actually measured it to be 1.5 sources per day. And at that rate, the chances of finding 2 FRBs that are closely related in sky position and DM is non-negligible. And you can see here from Amanda's paper, we developed a statistical framework to say how likely it is that 2 things are aligned by chance. And you sort of see in the heat map here that towards higher declination and at lower or sort of moderate DMs, the chances are highest of finding 2 FRBs that seem related but are not. So we worked out this framework, and we do manage to detect a lot of repeating sources. About 3% of our FRBs turns out to be repeating. And you can do nice things like monitor them. This is a figure from a recent repeater discovery catalog. And you can see the different lines here are different repeaters, and all the colored dots are detections. So we can track things like their activity over time. In terms of characterizing the intensity data, so this is the beamform data that we do the FRB search on. This is a less intensive data product to store in terms of its volume. So we have about 1 millisecond time resolution and 16,000 channels over 400 megahertz. We developed this framework to do burst fitting, which we call FitBurst. This is telescope receiver agnostic. So if you have some data from your telescope or your receiver that you'd like to fit, it should be able to work. But please reach out if you encounter any difficulties. On the left, you see an example of one FRB from CHIME on the left, the model that FitBurst comes up with in the middle, and then the residuals on the right. We also do flux calibration, but as you've maybe seen, if you try to use the flux influence measurements from the intensity data from CHIME, these flux limits should be treated as a lower limit, and that's because there's a little bit of a degeneracy because of how the beams are formed. And so this figure shows some slices to the beam model, and you can see on the left for different beams the sensitivity in the east-west direction. So you see there's some degeneracy between a brighter FRB being detected in the side lobe or a less bright FRB detected in the main lobe. And that we cannot solve with this data. And on the right in this image, you also see that this is a chromatic effect. So you see these side lobes here with the different colors, they appear at slightly different angles. So we do apply flux calibration to our intensity data, but these are the caveats. We can do a much better job if we have the voltages. And so now we managed to save the voltages also for a very significant fraction of all of our FRBs. In this case, we have 800 megasamples per second for the data. We can't do PFB inversion. Those are some technical details that I'll be happy to chat more about if you're interested. And we can do with the data is we go from about a 10 arc-minute localization accuracy to about an arc-minute on the sky. And you can see this in this figure where the blue contours show the best we can do with the just with the header data, the real-time detection. And then this red cross here shows the accuracy we can get with the voltages. So it's much better. And it also solves the degeneracy between the different lobes of the sensitivity. Then we can also get to microsecond time resolution. And here's the most dramatic example that I know of, where you see the difference between the 1 millisecond time resolution on the right and the microsecond time resolution on the left. So you see much more burst structure that you can use to learn about the emission physics. We can also get the polarization information. We can get Faraday rotation as well. And now if we measure the fluxes with the voltages, then we are able to resolve the degeneracy in the position. So we know where in the sky the FRB is coming from to enough accuracy that we can actually measure the flux instead of providing a lower limit. And here you see the comparison between those fluxes from the baseband data or the voltage data on the vertical axis versus the intensity fluxes. Then another feature of CHIME is it's doing a deep main lobe survey, but it's also doing a shallow side lobe survey. And this you can see best in the figure on the right. This is showing the sensitivity of the CHIME beam as calibrated by some bright radio sources. And you see out to many tens of degrees, we're still sensitive to the sky at about a % level. And so, for example, this FRB-like burst from SDR 1935 on the left was detected 22 degrees away from the meridian because of the sensitivity still at those hour angles. And then we also found, at least we published so far, 10 of these very far side lobe FRBs. So as a population, we know these must be 500 times brighter. And so that implies they're 20 times closer on average. And so that's also setting interesting limits on the repetition rate of these FRBs because we're very often on the sky in the side lobes. Then we try to characterize our selection effects. So one way of doing this is we do injections in our detection pipeline. And so this characterizes our sensitivity. Here you see one example from Marcus Merrifield paper showing the fluence versus the width of the injected burst. And so the color here indicates the fraction of injected burst that we recover. And so you see we lose a lot of sensitivity towards lower fluences and higher widths. We also know there's some chromatic beam effects, especially in our intensity data. And so this figure shows if you detect different bursts from the same repeater, in this case, FRB 20180916B, we know that if we detect them outside of the main lobes, we are biased towards detecting narrower frequencies. So this is something to take into account if you want to interpret those intensity data. To be more sensitive to the broader burst and maybe to long period transients as well, we're developing now CHIME Slow. And so you'll see more talks about this later on the conference. And the next revolution we're trying to make happen is using outriggers to really zoom in on a lot of FRBs and also find host galaxies and the position within host galaxies. And so for the main CHIME station, the best we can do is probably about an arc-minute, which I overlaid here roughly on the Hubble Deep Field. But now with the outriggers, we can get down to about 50 milli-arc-second localization. So then we can tell which of the galaxies the FRB is coming from and where in the galaxy it's coming from. All of these telescopes are now built and operational. And just some details, because this is a pedagogical day today. We're doing very sparse sampling of the UV planes because we only have 3 baselines, 3 telescopes with CHIME. And so we don't do traditional imaging as you are maybe used to from VLBI. But what we do is direct fitting of the delays to the visibility. So what we're interested in is fitting this function from the visibilities between all the baselines. And what we're after is this geometric delay tau, which gives us the position of the source on the sky. But we need to correct for the effects of the ionosphere, as Kelvin already explained this morning. And so how this works in practice is, here's a nice diagram from Xion, is at each station, we first need to align the wavefronts. Then we need to do de-dispersion because FRBs are de-dispersed. And then finally, we need to identify or gate on the transient, so we don't correlate the noise, but only the FRBs. And then eventually we form the visibilities on all the baselines. And then those visibilities is what we actually fit to get out this geometric delay and this delta DM term on the different baselines. And so here's an example of how this then looks like. This is for the one-off FRB that was localized with the pathfinders for the Outrigger project. So 10-meter dish in Algonquin and a dish at Greenbank. And so you can see here also the multimodal aspect of these localization that Kelvin already discussed. And so you see here what we're fitting is this, the RA, the DEC, and this delta DM term for the 2 baselines in this case. And so that's how the localizations are produced. It's not through direct imaging. And the way we validate this is from the commissioning paper on the first Outrigger telescopes, the KKO one. We can look at many pulsars, many pulsar pulses, and we localize them. And for those pulsars, we know the localizations, and we compare our CHIME Outrigger localization with the known position. And we see that this matches in most cases, and we can characterize our uncertainty. Yeah. We've also started doing this for science. And so with one baseline, we already published or are in the process of publishing a host catalog. We can also do it for repeaters. This is for one baseline, multiple bursts, and you can see from the different positions of the day, the times of the day you detected, you actually constrain the position a bit better. This is from using 2 baselines, and Maassen will talk about the first result where we use the full array. And so in terms of catalogs, what we've been doing is presenting an intensity catalog, then identifying the repeaters, then updating it with voltage data, and we'll have to think about how we do this with including the Outrigger data as well. But the second catalog of intensity data will be published very soon, hopefully. And I'll just leave you here with some thoughts about the strengths of CHIME and the outlook, and I'm happy to take any questions.
Do we have any questions? Yes. I don't know where the cash box ended up. Okay, we bring it down like 4 rows. Sorry, I don't know. Nice. Can you please introduce yourself as well?
Hey, thanks for the really interesting talk. I'm Pawan. I'm Pawan from Swinburne Uni. I was just curious about the statistical inference about the number of repeaters that you're finding. Does that change the percentage of repeaters that you already have, especially using these clustering methods that you just mentioned about?
Yeah, so far we haven't seen any evidence for a turnover, so it seems to still remain around 2%.
Thanks.
We actually don't know. Okay, Laura, if you have us a really quick one. Okay. Oh, sorry. Everyone starts off very confidently and then realizes they can't actually.
It's Laura Spiller. Very quick question. So now that you have the CHIME outriggers, do you have a policy for updating the positions of repeaters as you get better positions from the outriggers, so that we can, for those of us who are interested in following up with, say,
yeah, we haven't really answered all those questions, but it comes back to sort of like our way of doing the data releases. I think we have to rethink a little bit how we do this going forward and what's the best way to help the community and science forward. But if you have any ideas, please feel free to talk to us. What's useful for you?
Cool. Yeah, let's thank Ziggy again. So our next speaker is Casey Law, and he's going to be talking on behalf of DSA 110. Sorry, I had DZA in my head.
Does this sound okay? Yeah, good. Thank you. Okay, I'm Casey Law. I'm a staff scientist at Caltech. Also have an affiliation with the Owens Valley Radio Observatory, which is operated by Caltech. And I'll be presenting a summary, a technical summary of how DSA 110 works and how you can benefit from what it's done. I also helped build the real fast instrument at the VLA. It's a separate topic, and if you have questions, I can answer those separately and over coffee, perhaps. So this is meant to be really a technical summary, so I don't dive into the science so much. But I wanted to quickly give acknowledgement to everyone that worked in the project. It's a large team. It's largely based at Caltech and Overo, but it is nonetheless a large team that worked hard over several years. Two people from the science and commissioning team are Jacob Faber and Miles Sherman, both of which will be here this week, but both of which had travel delays. So I hope you will connect with them tomorrow or soon after when they arrive. Very high level summary, just to give you a sense of the punchlines of what this instrument can do and what it's all about. It's really the first purpose-built FRB localization machine. So it's an interferometer that was built for this reason. And up until recently, that was the only instrument that was purpose-built for that reason. It's located at the Owens Valley Radio Observatory, so it's about 4 hours north of Los Angeles. If you find yourself visiting Caltech or Southern California and you have a free day, it's really worth the drive. It's a beautiful part of the state and a part of the West. And what distinguishes it is really this combination of wide field of view and good localization precision. So the wide field of view is really is designed to maximize the survey discovery rate. And the localization precision of about an arc second or so is defined by the longest baseline, but it's really targeting the fact that that's the scale of a galaxy, right? We're trying to associate the FRBs to their host galaxies, and that's what this instrument was designed to do. We're centered at the L band, so relatively small bandwidth, for modern instruments, I would say, but it is in this really productive and marginally protected band. Actually, I'll come back to that a bit later. And the search time scales range from 260 microseconds. And with the recent expansion that I'll describe, it goes up to longer time scales, up to 20 seconds. And that's the subject of this not so fast radio burst project, which Miles is developing. Much as CHIME and others have been practicing, it's a real-time search triggered recording for offline analysis. So it's this sort of two-stage. You break up the problem into search and then analysis. And you can bridge that gap by having large buffers of data that hold the data while you are prospectively doing and looking for the FRB. If you find no FRB, then you just throw the data away and you move on. The timeline, this might seem like a nuance, and a little, but it actually is important to understanding where the instrument is today and where we're going. So it really started back in 2018 and was constructed in stages. So there's 2 big stages here, and you might know a lot of the science that's come out really from only half of the array. So that's the 63 antenna array, which was built during COVID, actually, which was an ordeal in itself. The team is shown here that was doing the construction. I want to acknowledge them because they actually worked in full PPE during construction in the desert of Eastern California. They actually received a commendation from Caltech for their extraordinary service to the Institute, which is remarkable. Early science operations have been conducted over the following 2 years. So that includes basically all the publications you've seen thus far. That's the sample of 60 odd FRBs. If you go to the DSA 110 public archive, which is basically a light little webpage with a table and links to some DOIs to download data, that shows 48 of those which have been published. And there are a handful more which have not been published yet, but are undergoing some analysis. Over the last year, so 2024 essentially, we brought the array down and we were installing another set of antennas, which was essentially adding collecting area. but it also modified some aspects of the digital system. So I'll talk a bit about that. And since 2025, we've conducted science operations again with sort of the completed array. So that's something I'll dive into at the end as well. So this soon aspect here, right? DSA 2000 is a much bigger project. It's actually in many ways totally different from DSA 110. And that's something that's really going to come to dominate what we're doing at Caltech. We expect soon, or we hope soon. So I'll talk about that more over coffee as well if you're interested to learn more about that project. So thinking about how you might be interested in learning about the DSA 110, how you can use it, benefit from it. The novelties are really the fact that it was one of the first to really reduce the cost of the individual elements of the array. So maintaining this high survey capability through wide field, high sensitivity surveys requires you to have a combination of relatively small apertures, but also very, very cheap low noise amplifiers. So that's what this little inset shows. So Sandy Weinreb is a early innovator of the field, and he developed this low amplifier as a system temperature, or a temperature, receiver temperature of 7 Kelvin. It's extremely low because it's uncooled. It's really remarkable. Another distinguishing feature is that it's only steers in the elevation axis. So again, it's very cheap, but relatively simple. And it has this core plus outrigger layout, which again is quite common nowadays. But the core is what conducts the search, and the outriggers have this data recording capability and a buffer. I'll highlight here the yellow lines show the core. So there's a sort of a T, we call it. So there's a concrete pad there that existed for prior arrays and work. So the millimeter array, for example, you may know, which is a part of Karma. You know that. It's before ALMA, anyway. So the east-west array was what was populated during the 48 antenna era. The north-south part of that array was what we built out over the 2024 year to make this 97 antenna array version of the array. And the outriggers were there the entire time. So that was part of the first phase. So all those outriggers were part of the analysis system from the first construction phase. So the real-time search system, don't need to go into a lot of detail here, but it's an FX correlator design, which is produces both beamform products for the search system. So there's 256 beams along this east-west axis, 256 beams along the north-south axis that's formed from the east-west and north-south antennas that are in that T shape. So those 512 beams go into a search system, and we have an algorithm which tries the coincidence and threshold on that stream in order to decide when we should trigger the recording of voltages that are in that buffer for all antennas. And then in parallel to that, you notice this middle arrow here that goes, there's one that goes to the NSFRB search system. So that's this roughly second scale transient search, which is an image plane search with moderate dispersion. It actually does search over dispersion space, but it's a relatively low computational intensity in that case. And then on the bottom channel there is an imaging and calibration pipeline. And that includes actually something that Jacob Faber is working on, which is an ESE scattering, stream scattering event search algorithm. So when we find things, we have a triggering process, which is that box sort of on the top right roughly. And then that's where we make the decision about sending alerts to the community and also sending data to our public archive. So the rough process here, just to go through it in detail, is the search system, that whole, everything I described to you is in that top left box there in item 1. So discovery, confirmation, and analysis in that entire graph I showed before. The offline analysis relies on applying the calibration from the image plane and doing astrometry. And we use that fundamental radio catalog VLBI reference field for calculating offsets and correcting for calibration, residual calibration errors. And then we'll have an image plane that looks something like this with that T plus the outriggers. We have a kind of a weird looking PSF. And so that has these really strong low PSF low side lobe patterns. But you can clean it up pretty well. So the bottom left panel shows how it cleans. And then on the bottom right, we see the offset distribution when you apply the same imaging algorithm to the VLBI sources. And you get generally a distribution of offsets, which gives us some confidence in how well the localization works there. This is, I would say, a pretty good scenario. Doesn't always look this good, but that's kind of how they tend to look. And so my last slide is just to highlight the things that we're producing in the completion stage. So once we get things really rolling with a completed array, we have now we have a minute latency arc minute precision alert stream. So that's something we've already used to send alerts to the Swift Guano system for rapid follow-up. And that's something that we intend to make more open. We also have an analysis system that Miles Sherman built, which does sort of in-depth interactive analysis of the burst data. So scattering, polarimetry, all the good stuff. Those results can be packaged into alerts and messages we send out to the community. Filter bank files, the classic data product that will be served on the public archive. It's actually not there presently, but we'll get to that this week. And localization regions. So this is, of course, how we do a lot of the science. So we have this arc-second scale localization, in this case, shown against a massive, massive galaxy to make it look really, really precise. But generally, we have galaxy scale localization regions, which are really helpful for helping us think about, well, do the association to measure distances, but also think about the source origin problem. I'll make one final comment, which is that we have been observing in 2025 with this completed array, our rates is not where we expect it to be also, which maybe is a theme for many of us. And we're digging into it. It seems like we might have a problem with a new source of RFI, which is really kind of peculiar. And we're digging into it. It might be like out-of-band RFI. So it's something that we're not fully understanding yet. And that's limiting the rate at which we're identifying new FRBs. If that gets resolved and we can filter it out, that means we'll be actually doubling the rate of discovery from the initial stage of the array, roughly doubling. So that's where we hope to be in the next few months. So keep your eyes open for those alerts. Thank you.
Thank you, Casey. We have some time for questions. Mawson, where's the, Laura has the catch box. Can it come this way, please? Someone take one for the team. I like that. Yeah. That's even worse. That's got to be a lot, right?
Hi, Casey. It's Mawson Salmons from here at McGill. And it was a great talk, so thank you for that. The kind of question that I had was that given that there is some through theme about not meeting like the desired specifications for like FRB rate and that RFI might be having an impact on some of this, in like trying to tackle this problem, do you think it's worthwhile to like have a few different instruments out there publish like wide scale studies of the RFI that they actually observe and put that out in the community as like a data catalog for people to help train on or help mitigate with new techniques?
Right. So the question is, would it help for instruments to publish RFI surveys essentially from their own, from what they see? Yeah, I could imagine there's a lot of value there. RFI does, there's certainly many classes of RFI, and many in cases they tend to be local. We actually, for DSC 2000 purposes, built a portable RFI monitor, which is out in Eastern Nevada right now, surveying the site. We didn't want to take for granted that we could, Starlink would tell us, exactly how it behaves, or the mobile phone companies would actually know what they're radiating. But in terms of ML-based, techniques or filters, I think there's a lot that can be done from real data that we measure. If we can make it, there are open source classifiers with various flavors, right? And convolutional neural networks that will look for sort of real bogus-like classifications. But they would certainly be improved with more diverse RFI categories.
Great, thanks.
Any other questions? Okay. Oh, Kelly? Give it a wall.
Who's in the middle?
Nice throw. Yeah, Kelly Gorgie from CSIRO. So you'd mentioned extreme scattering events. That was really interesting. I was wondering if you could say more about what specifically, yeah, what sort of observables you're looking for in your data stream to flag that, and what you plan on doing with it. Because I think
that was a teaser. See if
Yeah.
it worked. Jacob will be here this week, and he should really be the one to tell you all about it. But it is essentially doing deep imaging with the DSA 110. So full cross correlation of all antennas. You know, hours long integration to make very long, deep, wide maps, and then repeating. So it's a transit instrument, and we'll just continue to monitor daily. And then there's follow up also. There's a follow up aspect to it, but. Yeah.
Thanks.
Let's thank Casey again. So the second half of this session is going to be entirely online. Unfortunately, due to some last minute travel issues, our next speaker was unable to join us in person. So our next speaker is Chenhui Niu, who is talking on behalf of the FAST collaboration. That is not.
Okay, it's my screen.
Yeah, we can see your screen.
Thanks, Lauren.
Yeah. No. Oh, you got the background.
Is this fine? Okay.
Yeah. Okay. Yeah. Take it away. You have 11 minutes.
Thank you. Hello, everyone. This is Chenhui Niu from Central China Normal University in Wuhan. Sorry for not being able to be in person this time due to my visa problem. It's my pleasure to introduce FAST here. Just to notice, my talk is on behalf of the FAST FRB Key Science Project collaborations. This is our logo. My talk will include 3 parts. For the FAST overview, the introduction for the FAST proposal call, the FAST program on FRBs. As most of my slides use a full screen layout, I will try to turn off my camera a little bit. Right, anyway. So in 1993, the International Union of Radio Science held in Tokyo. During the conference, astronomers proposed to build a next generation large telescope, which later known as the ASKAP project, aiming to construct a very big telescope with a total collecting area of 1 square kilometers. Upon hearing this news, Narendong, who is the father of the FAST, was very inspired. He began planning to build the large radio telescope in China. He began the road to build China was full of challenges. Beginning in 1994, it took 12 years to take the site selection. And FAST was officially proposed in 2005, and after overcoming lots of technical difficulties, the telescope construction was completed in 2016. So image here shows the original FAST site, natural cast landscape with 12 local residents. So animation here shows the construction process of FAST. As Narendong once said, the best astronomical facilities are in fact built for the next generation of astronomers, for the young people who are studying now and those who will enter the field in the future. So we are the lucky generation. Okay. So first take a lot of appearance from Arispo. So the photo on the left bottom shows Narendong and Chenhui, who was 2 FAST founders. That's a trip to the Arispo observatory in the early days. So image in the upper left shows the FAST alongside with the world famous Arispo telescope. Unfortunately, the Arispo collapsed in 2020 due to an accident. First, continue the science from Arispo. The image on the right shows the scale compared with the world's largest telescope, offering a sense of a fast, impressive size. So first achieved a lot of innovations. It has a 500 diameters, that feature an active reflector surface composed of 4 sound panels that dynamically adjust to form a parabolic shape for each target direction, greatly improving the pointing flexibility. Its feed cabin is suspended by 6 cables and controlled by the computer. So the faster feed cabin weighs up to 30 tons. So its positional control achieves accuracy of within 4 millimeters. It's very impressive. So 30 tons within 4 millimeters error. So FAST not only get scientific achievement, but also makes the local economic development. The area within 5 kilometer radius of FAST is dedicated to the radio quiet zone. And the residents there near in the 5 kilometers will move to the Kedu town, about 5 kilometers away from the FAST center. So government built a lot better housing for them, and with fast tourism is bloomed. And astronomy town also was built in the Kedu town. It has restaurants, the hotels, and the science museum. We hope the FRB conference can be held in China next year, and so that everyone could visit this place. So based on its bandpass, FAST has its scientific goals when it has been established. So including the H1 detection, the discovered pulsar like the PDA, during the international WLBI network, perform high-resolution spectrum survey, detect the weak space signals, participate in the SITE. As it is proposed in the early years, FRB is not one of its basic scientific goals that time, but it added later. So this scientific goals has been realized by the observation programs. FAST has been supporting the regular science programs, the medium science programs, and large programs. Over the past 5 years, the large programs used to call the Key Science Project, covered 6 main projects. Each project have hundreds of hours to do its main science per year. So there are 3 science projects that are related to FRB. It is the Commensal Radio Astronomy Fast Survey, the Galactic Plane Pulsar Snapshots GPPS survey, and the Fast Radio Burst Search and Multi-Wave Observations. The last one is the most concentrated on the FRB science. So except the large program or the key science project, most researchers are likely to take the general proposal call to perform your own target. The general proposal call start from the March to May each year, and the result will be public in August that year. So you can find the link there. It's the official website for the FAST. It should have both Chinese and English, so it doesn't have any difficulty for the understanding the website. All the for the regular science proposals, it will have up to 50 hours per proposal, and for medium science is observation times span from 50 to 150 hours. So each proposal will be peer-reviewed and judged from the tech. CRAFTS as one of the fast key science project or the large program, it was proposed by Dili using the high time frequency calibration injection technology. It could perform a pulsar search, the spectrum record simultaneously. So during a scan, CRAFTS also discovered a large number of pulsars. With 200 new pulsars were identified, including many in binary systems and millisecond pulsars. For the fast radio burst, CRAFTS has discovered 9 new FRBs, 5 of these FRBs have been published. Of the FRBs have shows low luminosity and high DMs, reflecting the new FRBs come from the early stage of the universe if we using the DM budget to calculate the redshift. Kraft also reviews a high FRB outscale event rate, higher than 10 to 5 FRBs per day above the faster threshold. So GPPS is also a large program. It is a high sensitivity, large area radio survey conducted by FAST along the galactic plane. It is using the snapshot mode to search for pulsars and radio sources. During the galactic plane survey, GPPS also discarded 8 FRBs and 1 FRB candidate. These sources exhibit high DM and low fluence. So the largest FAST contribution in the field of FRBs come from the FAST Key Science project, FAST FRB Key Science project, a dedicated large program specifically for FRB studies, led by Zhu Weiwei and Zhang Bing. Also, FAST has very high sensitivity. It's a small field of view, takes a less advantage for discovering new FRBs for the blind search. Instead, it is good at the follow-up observations of FRBs. For example, after the CHIME detected FRB, a new source, a potential repeater, FAST perform follow-up observations. So the list here are the active FRBs that are FAST frequently monitored by the FAST KSP, FRB KSP. The KSP holds regular weekly meetings to discuss the follow-up observation strategies and the data analysis to the active FRBs. Usually, an interesting source is started from multiple scientific goals, so the leading to a series of publications. That's a general work style of the FAST FRB KSP. So there's a case for the KSP work style. So for the FRB 2020-11-24A, the very famous one, this source was initially discarded by CHIME and subsequently followed up by multiple major telescopes. During the follow-up observations, FAST detect a high event rate and get a large FRB examples, and uncovered a highly dynamic and variable local magneto ionic environment. So this was proposed by Xu Heng, who is also a member of the KSP. And so the key findings was published in Nature in 2022. And however, the analysis of these large samples extended beyond the initial science discovery, so such as energy distribution, the morphology, the periodicity, the polarization. Each of these studies was carried out by different researchers. So these complementary works were published simultaneously, providing a comprehensive understanding of FRB 2020-11-24A. The other case is for FRB 2024-0114A, the hyperactive FRB. So this source is another FAST FRB KSP collaboration case. So the hyperactive FRB has extremely event rate, and the total 10,000 bursts were collected. Junshuo Zhang led the discovery, and the paper is to be submitted. Alongside, there are several other papers focused on the different scientific goals, like the RM, the morphology, were also carried out simultaneously. FAST also conduct long-term monitoring of some famous active repeater, like the 1211-2, the first localized FRB. Using the FAST and GPT data and combined with the other major telescopes, FAST has revealed clearly evidence of a decade-long evolution in the local DM, and extremely the FRB and the complexity of the FRBs magneto-ionized ionic environment. So FRB 190520B is a source we discovered using FAST and have been continuously monitoring with FAST since its detection. It was first identified in 90 beam in drift scan survey of the crafts. So there are the 90 circles.
If that's okay.
Oh, sorry. Notably, it has a second non-FRB associated with a competitive PRS. So the related discovery has been published in 2022. So over the 5 years of follow-up observations by FAST, we found that this source has never stopped. So it remained persistently active. Although its burst rate is not that high, but every time FAST pointing to this source, it can detect has a burst detection. Additionally, we have found the 12 DM unit per year decreasing for the total DM. Oh, so a quick advertisement I will take later. So finally, I'd like to introduce China's efforts on FRB detection are not limited to FAST. Many other existing and upcoming facilities will bring new opportunities for detecting and understanding FRB in the future. And thank you. I hope we can see you in China next year. I'll stop here. Thank you. Thank you.
Thank you so much. Have we got any questions? Are there any online? No. In which case, I have a very naive one. You said on one of your slides that you have 120,000 daily events. And then you also said in the same slide that you have detected 9 new FRBs. So that 120,000, are they from known FRBs? What are they coming from? I wasn't sure I understood that.
Yeah, maybe make it confused. So for the ASKAP rate, FAST has a law of low threshold, the very high sensitivity. So above the FAST sensitivity, the around 10 million Yansky millisecond. So above that threshold, we have the 10 to 5 FRB event rate per day, but it's for whole sky. So FAST has a small field of view, so it doesn't have an advantage on the blind search, the FRB source.
Okay.
That depends
Thank
on
you so much.
how many. Yeah.
Oh no, Karen. Sorry.
It depends on how many sources FAST detected and using how many hours. But when you divide the field of view of FAST, very small one, so the event rate getting high, all sky event rate getting high.
Oh, thank you. I think we'll move on to our next speaker now. So if you'd like to stop sharing your slides. So our next speaker is Visweshwar Marthi, who is talking on behalf of the GMRT group. If you would like to share.
Trying to share my slides.
Yeah, so you have 11 minutes.
Okay.
And I will come and talk into the microphone when you're running out of time.
Sure, thanks. Well, good afternoon, and I thank the organizers for inviting me. I couldn't be there physically because of some family commitments, but I'm happy to be representing the entire GMRT community and trying to give a brief overview of the telescope and its usefulness in pursuing FRBs. So unable to advance to the next slide. Okay, there we go. So the GMRT is primarily an imaging instrument. As you all know, it's an array of 30 antennas, 30 dish antennas, each of 45-meter diameter. And these antennas are placed roughly along the arms of Y, with roughly half of them along the 3 arms, and the other half in central condensation called the central square. So, and what this gives you is baselines up to about 25 kilometer, which give you very high angular resolution. Whereas the short baselines, which are all packed in the central 1 square kilometer, gives you sensitivity to diffuse low surface brightness features. And so this was designed in this way to optimize both sensitivity and angular resolution. And so, this also means that it's primarily an imaging instrument. And like all synthesis interferometers, we use Earth rotation to synthesize a large aperture to fill the UV plane. And it has a very modern digital backend, which is an FPGA plus CPU, GPU based hybrid digital backend. And being an interferometer, it allows you to harness its power both as an interferometer as well as a beamformer. And it's also primarily a low frequency instrument, but it also gives you nearly seamless coverage from 150 megahertz to about 1.5 gigahertz with very few gaps in between, as you can see on the top right picture there. So the observing bands are, for ease, we just call them bands 2, 3, 4, and 5, but they're typically about, the lower bands are about an octave wide from 120 to 250 megahertz, which is band 2, and band 3, which is the more popular band, which is 250 to 500 megahertz. The most popular one is, of course, especially in the context of FRBs, is band 4, which is 550 to 850 megahertz. And band 5 is our L band, which is from gigahertz to 1.46 gigahertz. Band 2 is mostly written with RFI, and so it's not very frequently used. But bands 3 and 4 are typically very popular with those who study FRBs. And on the right-hand bottom, you have a plot which shows the sensitivity with respect to the other telescopes, which are commonly in use now. Although this picture is somewhat dated, the GMRT is still quite competitive in terms of sensitivity, and it's especially useful if you want to follow up FRBs which have already been localized. So the heart of the GMRT is, of course, the wideband backend, which is a digital backend. It's an FPGA-based sampler plus packetizer, but the rest of the operation actually happens on a CPU GPU cluster, and that's used for real-time FX correlation. So it processes 100, 200, or 400 megahertz of instantaneous bandwidth. There's also a narrowband mode for spectral line observing, which is achieved by a digital down converter, which is running on the GPU. The interferometer provides instantaneously about 450 baselines, and the plus 30 comes there because of the autocorrelations from the 30 antennas. So you have about 465 instantaneous baselines at any time. And typically you get about 2,000 to 16,000, 2K to 16K spectral channels with about a 5-second time resolution. That's for the interferometric visibilities. But there's a concurrent beamformer, which can give up to 4 instantaneous tide array beams. And the way these tide array beams are actually achieved is by phasing up the array using the phases, the antenna phases, which have been solved for from the visibilities themselves. So the visibilities actually provide the solution. So the interferometer has to be running in parallel for the beamformer to be functioning. So the main 3 modes for the beamformer are the phased array beam, which is the other name for a tide array beam, where the voltages are added and then squared to get the intensities. There's also a coherently dedispersed beam where the voltages are added in phase, and then it goes through the coherent dedispersion kernel. And then there's also an incoherent array beam where the antenna powers are added to get the final beam. And of course, as expected, the phased array beam is actually the synthesized beam of the instrument, which is much, much smaller. The incoherent array beam is as large as the single dish beam itself. And the coherently dedispersed beam is, of course, the same as the phased array beam in terms of angular size. And we've actually been consistently working on upgrades to the GWB almost every time allocation cycle, and some of the new modes which have been unlocked are the in-field phasing, where point sources within the field are actually used to phase up the instrument, so you don't waste time going on to another phase calibrator, so it actually reduces your overheads. There's now also a gated correlator, which is useful for pulsar studies. A new high time resolution visibility mode is now available, which can give you visibilities at 83 milliseconds. There's a multi-beam recorder with 4 synthesized beams, and this is the mode where you can actually look at 4 different sources within the primary beam, which is very useful if you want to do follow-up on FRBs, as well as also VLBI. There's a post-correlation beamformer, which I have not listed at the top, but there we actually sum the visibilities instead of the antenna voltages. And then we also provide full Stokes beams available for the phased array. And then there's a new coherent dedispersion mode, which was quite challenging to implement for the full 400 megahertz at band 5. There's also a baseband beamformer up to 400 megahertz, which is now being used for VLBI. But the baseband itself can also be used for niche science. And what's coming up is a parallel backend, which will give you the per antenna baseband. So for every antenna, one's going to get the full 400 megahertz baseband. Good luck dealing with the data, but that's definitely in the works. So what do we use the beam for? So in the context of FRBs, the phased array beam is best used if you want to follow up already localized FRBs. For example, this is a proof of concept localization of FRB 1809-16B, where the GMRT was used both as an interferometer and the beamformer mode to study the bursts, as well as to prove that the concept of localizing FRBs simultaneously is actually quite effective. So, here is another example of using the GMRT in the incoherent array mode, where once CHIME locked on to this 2020-11-24A with a lot of these ATLs coming out, many telescopes around the world were looking at this interesting FRB. The GMRT at the time did not have the precisely localized position of this FRB. So we just used the fact that it is only localized to within about 40 arc minutes, which is exactly the primary beam of the GMRT. And so we had to use the telescope in the incoherent array mode, where the entire primary beam is accessible through the beamformer. And so
you have 2 minutes left.
Thank you very much. And so we were also able to localize the bursts here, and also detect persistent radio emission, which is also out as an ATL. And of course, the full Stokes mode, which has been very useful, and Surya Rao has actually done some very nice polarization work, and that's the figure on the right, where you can actually see the GMRT points following the polarization of this particular FRB after the secular evolution, which was reported by Ryan McKinnon et al. So this paper just got published recently. And on the right, of course, you have more results from using the tide array in both the multi-band and multi-subarray mode. So this was, again, baseband data was recorded, and this paper gives you the results as from that particular analysis. And many of you might have heard in previous editions of FRB. I think it was the last one in Thailand, where my colleagues have actually put together this wonderful system. It's called Spotlight, which is a real-time commensal search program for FRBs and transients. In its full glory, it will give 2,000 beams with 4K spectral channels and about a few millisecond time resolution visibilities. At the moment, you can actually apply for competitive time using the Spotlight system, and about 100 hours of time is available per cycle. This will also dump baseband based on triggers, and which can be actually used for VLPI localization. And there's already some understanding between Spotlight and Burst, which hopefully will help localize many FRBs. And the first light has already been achieved. So we already have a system with 160 beams. And what you have here is just showing how the Spotlight system is organized. And so yeah, so this is just a brief overview of how the GMRT can actually be used as an instrument, primarily for following up FRBs. It's quite sensitive with the wide bandwidths, and it's also a versatile telescope. You can use it as an interferometer, as a beamformer with multiple modes, useful for deep observations. And several publications have actually come out of such observations. So at all frequencies below 1460 megahertz, it's quite effective, sensitive, and multi-band, multi-subarray observations, multiple beam modes have actually enabled some very, very interesting science. And of course, one now can also record baseband data up to the full 400 megahertz at band 5, for which the best application is VLPI for localization. And of course, Spotlight is coming up, and we're all quite excited here to be able to, we hope that in the next few years, we'll have quite a few FRBs through this commensal program. And so, we're looking forward to that. Thank you very much.
Thank you so much. Do we have any questions in the audience? Kyle. Okay, Catchbox.
Or from behind.
Or someone.
Somebody in the middle, maybe, heads up. Pavan?
Yeah.
Yeah.
Okay.
Hello. Kyle McGregor. I'm a master's student here at McGill.
Can you maybe turn around so everyone can hear your lovely question too?
So I was curious if this Spotlight search is going to be using all 5 frequency bands of GMRT, or if it's just using the 2 specifically that you said like to be used for FRBs within. So it was like 250 to 500 and then 550 to 850.
Yeah, so it'll primarily use bands 3, 4, and 5 for the simple reason that band 2 is just full of RFI. But remember, this is a commensal program. So any observation that's looking at any part of the sky, Spotlight is going to be observing in parallel. So it's a commensal program. But there are also some policy issues which have been addressed. And you can actually find some information about that on the Spotlight webpage.
Thank you.
So it's primarily going to be bands 3, 4, and 5.
Awesome. Any other questions? Cool. In which case, we would all like to thank you again.
Thank you very much.
So our penultimate speaker of today is Kaustubh Rajwade, who is going to give us an overview of the MeerKAT radio telescope and what it's been doing for FRBs. Kaustubh, I'll give you, you have 11 plus a bit minutes, and I'll come and speak into the microphone when you have 2 minutes left.
All right, thanks. Can you hear me?
Yes, we can hear you.
All right, perfect. Yeah, thank you so much for giving me this opportunity to talk about the MeerKAT project. Yeah, I'm sorry I can't be there in person, but I'm more than thrilled to give you an overview for this project. So yeah, I mean, I don't think I need to really motivate too much about why we need to study FRBs, but I think one of the points I would like to make here very quickly is that I think it's quite important to find FRBs, that are much further away at much higher redshifts, not only to, break the degeneracies between different emission models, but also kind of really realizing their true potential as probes of cosmology. And so it absolutely makes sense to build a real-time FRB detection instrument at the MeerKAT radio telescope, which is one of the most sensitive radio telescopes currently operating. So MeerKAT, for those of you who don't know, is a 64 dish radio interferometer in the middle of the Karoo Desert in South Africa. And MeerTrap actually works commensally, which means that any data that are being taken with the telescope are being continuously looked at and searched for FRBs and other fast transients using a pipeline that I'll go through in the next few slides. But before I begin, I would just like to talk about the collaboration. So MeerTrap is mostly led a University of Manchester-led project. Ben Stappers is the PI, and the collaboration includes a lot of teams from Max Planck in Bonn and University of Oxford, and we got a tremendous amount of support from Cereo during the commissioning and testing phase of the system. So just want to give them a massive shout out. And of course, we collaborate pretty closely with the F to the 4 collaboration for following up our discovered and localized FRBs. So in the previous slide, I mentioned commensal observing. So what it means is that the telescope is being used by many different projects. So when MeerKAT started science operations, it was mostly focusing on these large survey projects that have been given an incredible amount of time on the telescope. And so these projects have been running now for a few years now. And what it means is that we're basically getting a huge chunk of observing time on sky with the MeerKAT to look for fast radio bursts. And so just a lot more opportunities, a lot more, more discoveries to look forward to. So by the time the LSPs end, we'll roughly would have had 20,000 hours of observing time, and even more, which I'll talk about later. So MeerTrap predominantly works in 3 observing modes. So there's the incoherent mode, where you're taking the detected parts from all your antennas and summing them up, so to sample the entire primary field of view of the telescope. But it does mean that it's not the most sensitive search. And so the sensitivity we get from that kind of a search for FRBs is comparable to what you would get from a 64-meter single dish like the Montréal radio telescope in Australia. In the coherent mode, simultaneously, while we do the search over the full field of view, we tile some part of this field of view with smaller but more sensitive coherent beams or phased up beams. And so because of compute limitations, like I said, we're not able to tile the full primary field of view, but we roughly can do a more sensitive search for FRBs in that 0.4 square degrees of the sky. And it uses the 40 core dishes of the MeerKAT array to make these beams. So you can compare this search to something that you would do with a 100-meter dish like the Green Bank telescope in the US. And then lastly, we also have this mode where, if we find a discovery, or if the real-time system detects an FRB, it triggers storage of these channelized complex voltages from every single antenna that's observing, which then can be processed offline, not just to actually localize the FRB in order to identify the host galaxy, but then also do some high time resolution and polarization studies. So just to quickly give you a brief overview of the pipeline. So the beamformer, the actual beamformer, has been developed by our colleagues at the Max Planck Institute in Bonn, which generates these 768 beams, and these coherent beams along with the incoherent beam, and those are then received by the MeerTrap compute cluster, which is made up of 65 nodes. Each node then basically processes to about 12 coherent beams in real time. And the single pulse search is done by a GPU-based algorithm called AstroAccelerate, which was built as part of the SKO single pulse search pipeline prototype. And then we also have a machine learning classifier, which then tries to identify the candidates as whether they're astrophysical or not in real time. Then, as I mentioned before, we have the transient buffer. So in the case that the real-time system finds or identifies a candidate as being astrophysical, we send out a trigger internally to the beamformer, which then saves the raw channelized voltage data from all these antennas, which is constantly being received on a ring buffer. So one thing we actually do is that when we save the channelized voltages, we actually take into account the dispersive sweep of the FRB. So which means that this is a huge help in terms of then actually it kind of overcomes the storage limitation that we have, because saving channelized voltages, as you would know, requires a lot of storage space. And so while we are able to save, about 30 to 50 seconds of data, we typically only end up saving about 300 milliseconds of data right around the time of the FRB after taking into account the dispersion sweep. Some of these, the key functionalities that we also have, the beamformer is really flexible. So what it means is that if we have multiple sources in the sky, we can actually create smaller tiles of coherent beams around these sources, just to follow up. So for example, if we have found something new, next time the telescope is observing the same field, we can actually put a separate tile of coherent beams there to follow up that source to just see if we can look for repeat bursts, or in case of a galactic source, just look for more bursts from the same source to maybe find the period. And also, we also have the capability of changing the overlap between, successive or just adjacent coherent beams. And this is quite useful if you want to also kind of quickly localize a source. So if you get detections in multiple beams, you can use that to get a very good localization, even before you actually localize it using the transient buffer. Now, we know that finding a multi-wavelength counterpart to an FRB is quite important in order to figure out what, to really discern the nature of FRBs. And so there's a lot of opportunity to do that actually with MeerKAT, because there is an optical telescope called MeerKAT based in Sutherland in South Africa, which is a fully robotic optical telescope, and that actually can co-point or tries to co-point with MeerKAT for simultaneous optical coverage whenever possible. And actually, very recently, we managed to achieve an almost contemporaneous optical coverage of one of the FRBs we discovered that I show here, which was localized to this nice potentially interacting galaxies. And this figure in the middle is just showing you kind of the limits, the optical limits that we got at the time of the burst. So there's still, so we have shown that this can work, and, we're still doing this and trying to see if we can actually get a fully contemporaneous optical coverage for some of our sources. So just to kind of quickly show you, so MeerKAT has been operational now for almost 5 years, more than 5 years. And so far we have found more than 110 new galactic discoveries, and keep finding more. Most of these, tend to be pulsars or highly intermittent rotating radio transients. But we've also found some interesting sources like this middle panel, which is a 17-second pulsar, which we're following up. And also, as you would know, we also discovered this 76-second pulsar about 3 years ago. And then we're also finding some single pulses that are showing a lot of interesting structure in their emission. And Jun Tian will be talking about this, in the coming few days. So please stay tuned for the results.
You have 2 minutes, Kaustubh.
Yep, thanks. We have found more than 80 FRBs over the last 5 years of our operation. More interestingly, I would say we have found about 25 high DM. So when I say high DM, DM of more than 1,000 kind of FRBs. And again, we're working closely with F to the 4 collaboration to for following them up at optical wavelengths as soon as possible to try to localize them, find their redshifts, because I think that's kind of one of the strengths of MeerKAT, in the sense that it is able to find these fainter and farther out FRBs. And so just to kind of end on the recent highlights, like I said, we're generating this sample of really high DM FRBs, and a lot of which we have localized to sub-arc second precision, which means that we'll be actually able to figure out what their hopefully what their host galaxies are, and then actually estimate a redshift for them. We have also recently discovered a repeating FRB. And so Kavya Saji, who's a PhD student in Australia, she'll be talking about it, I believe, in the next few days. And also, we have recently discovered this coherent radio burst from a galactic source from a known radio quiet neutron star, so which was really interesting, completely serendipitous. And so, so we can see that, there's a whole array of science that we can do with MeerKAT. And so Manisha will be actually will be giving a late breaking news talk on one of these recent results on one of the high DMFRBs. And also Ben will be talking more about some of these results. So please stay tuned for that as well. So I think I'm just going to end there with my summary. I think all I'm showing is that, I think in conclusion, I think MeerKAT has allowed for some detection of some, an array of fast radio transients over the last 5 years, and has utilized all the capabilities of MeerKAT. We have about 30% of our FRBs that we have localized to arc second to sub-arc second precision, and at the moment trying to follow them up and identify the redshifts for their host galaxies. And lastly, MeerKAT also runs commensally on open time projects on MeerKAT, and so people can technically actually use MeerKAT or can ask for MeerKAT to run commensally with their projects that they have running on the MeerKAT telescope. And this will continue to happen in the future. So thank you for listening, and I'm happy to take questions.
Thank you, Kaustubh. Do we have any questions in person? Amanda Cook. Sounded weird saying your full name.
Hey, Kaustubh. I was just curious, what sets the limit for how often you guys are able to do the simultaneous or near simultaneous optical follow-up with your FRBs?
Yeah, it really depends. Because firstly, it can only happen at nighttime. And so it's very, very weather dependent. And a lot of times there are also some I think we have just been a bit unlucky in the sense that we've had a few FRBs which were discovered during nighttime, but for some reason either MeerKAT was observing somewhere else or there were some technical issues with MeerKAT, and so it has just not happened. So this was the first time it happened. It got us super excited. So hopefully it happens a lot more frequently.
Yeah, thanks. Fingers crossed.
I have a quick question about your galactic discoveries part of your talk. Were they all found in the ThunderCat fields, or are they found kind of regardless? For context, ThunderCat is an X-ray binary / galactic transients program running on MeerKAT.
Yeah, so we mostly tend to find most of the galactic transients in the plane. So, and ThunderCat mostly observed in the galactic plane as well. But we also end up finding a lot of these transients in some of the pulsar timing projects as well, because a lot of the pulsars are also in the galactic plane. So any project that's mostly looking in the galactic plane, we tend to find a lot of the galactic sources there.
Thank you again. And also thank you for staying up so late to give your talk. Let's give a final round of applause. So our final speaker of this evening or this afternoon is Benito Marcote, who's going to be talking about the precise EVM program. Benito, you have 11-ish minutes, and when you get to 9 minutes, I'll come and talk into the microphone and give you a warning. Is that all right?
Okay, thank you. Perfect.
Nice background.
Okay, thanks. Okay, so thank you. I hope everyone is still awake and not too tired after the whole day. I'm sorry for not being there. I would have really loved that, but yeah, for different reasons, I had to do it online. So in any case, in this talk, I will do a summary of what we've been doing and what are we doing with the European BLV network observations on FRBs, and more precisely on the PRECISE project that uses these observations. And of course, I'm talking on behalf of the AstroFlash group that I'm part of and the PRECISE project. So the motivation of observing FRBs with the ABN started quite early when we really realized that having a lot of FRBs discovered was not enough if we really want to understand where they are originated and actually what's the environment or which formation channels may lead into the formation of FRBs. So to understand that clearly, we really need high resolution localizations of FRBs, and that's why we started conducted searches on FRBs using the European BLV network, which is an array of telescopes that are mainly in Europe, but also in Asia and Africa. And with them, we can reach millisecond resolution, and at least in the continuum, micro-Jansky sensitivity. So with that, we can be sure that we can pinpoint any FRB that we detect in our observations to the parsec scales on the host galaxy. So with that, we can really narrow down what's the local environments there. This is part of the AstroFlash group that is led by Jason Hessels. We are based in the Netherlands and in Canada. You can look at the website to see all the people that we have in our group nowadays. And we follow up FRBs with different approaches. I will talk and will focus only on the PRECISE project, which is led by Franz Kirsten, which basically lies on this, observing with the EBN disease. So this started with regular observation within the EBN, but of course, at some point we realized that we needed more observing time than the one that we were allowed in the EBN or that it has for the whole year if we really wanted to follow up a lot of the FRBs that are active. So with that, we started this project where we kind of use the free time that all the small dishes in the array has along the year. So we can actually spend roughly nowadays hundreds of hours per year, which basically is one observation every 2 weeks. And we follow up all the FRBs that are currently active, either because of a trigger following up the CHIME detections or any other observatory. So of course, when you are using such number of small dishes within the network, you can use them in 2 different modes. One is using them as just regular single dish telescopes. So we can observe the same FRBs from different locations, either at the same frequency or different frequencies. And the other one is the truly interferometric mode, where if we detect an FRB, we correlate with the regular correlator at JIVE from the EBN, and then we can perform the millisecond localization. So in the first mode, this is what we call the HyperFlash project, which in the last years we've been observing with these radio telescopes at different bands. And to put it in context, just last year with only Westerbork, we achieved almost 7,000 hours only in 1 year. So this allows us to do a big monitoring of active FRBs. In any case, I'm not going to go into details on these ones because tomorrow you will have a fantastic talk by Omar on this campaign and this project. And then he will actually show you why this is really important and everything that you can do with these small dishes that you cannot do even with larger ones, and what you can learn from FRBs from these observations. So just attend the talk tomorrow. In any case, this talk will focus more on the interferometric, the BLVI part. Until basically last year, there was a huge jump between almost all other telescopes that could localize FRBs, which in the best case scenario, they could perform localizations on their second level. So for the nearby FRBs, you could already pinpoint clearly the host galaxies, but this was not possible on the farther ones or fainter ones. So at least with our observations, we could perform millisecond level, which was like 3 orders of magnitude deeper in resolution than the other facilities. However, this has changed this year, and it has been really nice to see last week the first tens of millisecond localization given by CHIME. So now we have other tools that can actually localize these FRBs at this precision. Of course, this will be a new era, because with CHIME we will be able to get hundreds, thousands of FRBs on that regime. The difference with respect to precise is that we could still go a bit down to the millisecond level, and of course we have much more sensitivity, especially in the continuum regime. So to put it in context, during these years, we've localized and published 8 FRBs. And then from these ones, it was clear why we really need such a precision, at least in a number of FRBs. So our numbers are way far from what you can do with CHIME, of course. We are not talking about 1,000 FRBs, but we know that for a significant fraction of them, having millisecond relocalizations will be really relevant if we want to actually understand these sources. So this is quite clear in those ones that are related with PRS, a persistent radio source. We have a few sources that resembles really like twins because they are in the same host galaxy. Both of them are co-localized with a persistent and really compact radio source. And here, thanks to precise, we can actually put 2 really constrained measurements sorry, in these FRBs. One is on the compactness on these persistent radio sources. So to date, our most stringent limit is less than 0.7 parsecs for 121102. And this is really constraining upper limit that actually allows us, if we put also in context with the light curve on the 10-year time scales, what's the nature of these sources, because it still is completely not clear. And then by constraining the size and the variability that these sources may have is the only way that we can actually solve if this is superluminous supernovae, a magnetar with nebula, or just a massive black hole within the dwarf galaxies. So we see this trend in these sources that are quite extreme with high RMs, and by adding on new ones in the coming years, actually we will be able to trace if all the repeaters with PRSs are in the same host galaxies and how compact are these sources. However, identifying PRSs is not that easy, especially when you think that many FRBs are located in star-forming galaxies. So that means that in many cases we have radio emission just because of the star formation that either probably is in the vicinity of the FRB, either if it's inside or outside. And this is something that we really see that VLBA observations, like the ones that we've been conducted, it's really easy to disentangle this emission, because on the millisecond level, you are already on the edge where you will resolve out the star formation just because of brightness temperature limits. And that means that if there is a star formation, purely star formation emission, then all the emission will be extended. So you cannot see a compact emission that comes from that mechanisms. So in that case, we can confirm the existence of PRS.
You have 2 minutes, Benito.
Yeah. Oh, okay. Yeah. And of course, the other way is if you have a FRB that is either far, quite distant in a crowd field, or you have a very weak host galaxies. And this was a perfect case. So far is the faintest host galaxy, and it makes a perfect clear where you really need deep optical and radio observations to identify what's the actual true host galaxy. Because in this case, the FRB is associated to the 4 galaxy. It was not detected in normal, even from the Keck observatory. And then without the millisecond localization, any path analysis was actually linking it to a different galaxy. And the same happens in cases where we really see structures nearby, but then making the FRB placed outside or really in the vicinity of some formation of some regions actually makes a difference in the scenario that can explain it. So this is what we've been doing in the last years, what is upcoming in this year, basically. You may have seen a paper that you just submitted a few weeks, some months ago. This was the hyperactive 240114A, and then Mark did localization on this source, and this is the first time that we find an FRB in a dwarf galaxy, but then this is a satellite galaxy, actually. So it's a satellite of a more regular host galaxy that we see there. And another new localization, I will not go into the details here because tomorrow you will also have a talk from Alex that will actually reveal one of our new precise localizations. And stay tuned with this one because it's a really interesting case that we've been seeing again. So with that, I will finish here. With Precise, nowadays we are serving hundreds of hours, basically targeting active FRBs. And when we use the single DCs, actually we are on the regime of thousands of hours. So we're the instrument that can achieve both micro-Jansky sensitivity on the continuum and millisecond accuracy. So if we can place where the FRBs are associated with persistent radio sources, this is a key instrument. Nowadays, we are running through our regular EVN project, the so-called EVN Lite. And as Visweshwar actually mentioned in the previous talk, nowadays the GMRT is participating also in EVN observations, and MeerKAT will do it at the end of the year. So actually, we expect that we will be able to even boost more the sensitivity of these observations. And from the scientific point of view, we really think that this is key if we really need to understand the local environments on FRBs, given the diversity of environments that we are seeing, and especially if the most extreme cases, the ones with very high RM and dwarf galaxies are associated with PRSs. And I will finish here. Thanks.
Thank you, Benito. Do we have any questions? No. Matthias? Someone do the honors. That's going to have to stop somewhere in the middle. Oh, that was a good try. I reckon by the end of the week, we'll have this down like flawlessly. Yeah, would you like to introduce yourself and ask your question?
Yeah. Hey, Benito, it's Matthias. I was just wondering, what's the gain in sensitivity that you expect having MeerKAT join the EVN roughly?
Only with, there are two things actually. On sensitivity, we will be going down by 40% probably. Don't have the number in my mind, but I think on the 8 hours time scales, I think we will be able to go down to the 3 micro-Jansky RMS at L band. And the other part is that we win resolution, even if the baselines are not increasing, because we already have antennas on South Africa. Actually will allow us, especially on faint sources, to increase the actual resolution on the images. So in that case, we will be able to drop the levels, so the constraints on the sizes of these PRSs, hopefully to the 0.5 or even less parsecs if they are closer.
Awesome. Thank you.
And if we have